So now we're talking about probability distributions, and to understand this you'll need to know about fractions, permutations, combinations and N-choose-R, the binomial theorem, the Cartesian plane, and that's it.
And those things.
You okay with those things?
Yeah, we'll give it a go.
All right, so if we're looking at tossing up some coins in the air, so we're going to think first of all about probabilities of tossing coins. A lot of probability theory started out of gambling, which is why you tend to talk about cards and coins a lot, but they're quite a useful way to think about it. So if you just say, okay, what's the chances of throwing, well, how many ways can you throw 4 heads in a row or no tails? And you'd go, there's only one way to do that. Each time you do that, you have to throw a head. There's no options. So we call that the number of permutations. There's only one way you can get to that.
Right.
Now, if you're going to go, how many ways can you get 2 tails? Well, you can get them that way. Sorry, how many ways can you get 1 tail? You can throw on your first throw, your second throw, your third throw, or your fourth throw. There's actually 4 different orders you could throw and still get 1 tail. So we say that there's, for 1 tail, there's 4 permutations, or ways of doing it. We call that, the combination is 1 tail. The permutations is how many ways you could get there or how many ways you could arrange that. It's 4 times. Similarly, if we're going to go, okay, let's look at how many ways can you get 2 tails? Well, is that the first 2 times, not the first one, etc., etc. So there's 6 different ways you could throw 2 tails.
Yeah, okay.
4 different ways you could throw 3 tails, which is exactly the same as the number of ways you could throw 1 head. So it's going to sort of start getting symmetrical at this stage.
Yeah, of course.
And only 1 way to get 4 tails. Sorry, just go back there. Okay.
Yeah, that makes sense.
All right. So if we call that the number, just some terminology here. If we call those possible combinations in any study, we're going to call that the raw data.
So the raw data is...
The raw data is just what you collect doing something.
Whatever it is.
Whatever it is going to be raw data.
Yeah.
Number of tails. This is the number of successes. And again, this is partly because the language comes from gambling. But a success is whatever. I could have said a success is tails or a success is... But in this case, we're saying a success is a tail throw rather than a head throw.
Okay.
So
because we've just decided
that's what we want to look at.
Yep,
yeah.
Righto.
So the number of tails in this case is our number of successes. And once we take raw data and convert it to a number, we call that a random variable.
Just say that again.
Once we take raw data and convert it to a number, sometimes our raw data comes through as a number. Sometimes it can be anything at all. But once we give it a number...
So in this case where it's heads and tails, you're going to give a number to heads and a number to tails.
No, we're just giving a number to tails, which is all we're looking at.
Which is the only one we're looking at. Right.
And so we're going to call that x, and it's the same as the sort of variable we used when we looked at algebra, except it tends to be expressed with a capital X because it means this is a variable, but it has some sort of probability attached to it.
Okay.
Is the key thing. That's when it becomes called a random variable in statistics. We'll look at what a probability attached to it means in a moment, but just for now, it has a probability attached to it.
So in one short sentence, a random variable is
the result of some sort of research thing that you've looked at or question, converted to a number that acts in a certain probability.
Right. Okay.
It's a bit of a confusing thing because random we can think, well, that means it's all going to be the same.
Oh, okay.
It doesn't have to be the same. It just means there's some probability. The probability of different scores doesn't have to be equal.
Yeah. Okay. So I think random meaning anything could happen.
Yeah, it's a complex issue in statistics. And in fact, it's not well defined, and people do look at it differently. We explore that in some detail in the book. But you're right. It's a kind of... So what we really mean is we don't know what's going to happen till we throw the coin. We don't know what's going to happen.
Right. Okay.
Doesn't mean anything that could happen is an equal probability.
Yeah.
Just means we don't know what it is until we've done it.
So that's what the random element is.
Yeah,
we don't know until we've done it.
It's an unknown, but it is still subject to some kind of probability.
Yeah.
That's
as in the case of heads and tails.
Really good and really key point.
Yeah. Okay.
More terminology. This is called the support of the random variable. In this case, it's the integers from 0 to 4. what that means is this is the only values our random variable could take. If we're throwing a coin 4 times, it can't be 19.7. It can't be -3. That would be meaningless. So our support is 0, 1, 2, 3, or 4. They're the only possible outcomes.
Right.
Again, that's the terminology we use. Now, that number of permutations, or the different ways we could have got, different orders we could have thrown those to get to that, we describe as the frequency distribution. Well, technically we describe it more as a frequency distribution if we actually threw it that number of times, and that was the number of times it showed up, would be the frequency to have it. The probability, what we do is we divide the number of ways of doing things by the total number of outcomes. So 6 plus 4 is 10, plus 4 is 14, plus 1 is 15, plus 1 is 16. There's 16 different permutations we could get by throwing those 4 cards, those 4 coins rather.
Yep, makes sense.
And so we make a fraction. So we say to get 1, there's 1 chance out of 16. To get 1 tail, there's 4 chances out of 16, which is the same as a quarter. So we always talk about probability as a fraction, and normally we actually talk about it as in real life, we talk about it as a percentage, which is still a fraction. So 60% chance of rain today, or which is the same as 3/5 chance, or 100% chance that I'm going to get into trouble at work today, 0% chance. But we actually think about it as fractions, and so probability is always a fraction out of 1.
Yeah.
And in this case, by looking at the number of ways it could happen and dividing by the total number of ways, we get the probability of each thing happening.
Okay.
Which in turn means that all the possible probabilities are going to add up to 1. A 16th plus a quarter is going to be 5/16, plus 6/16 is going to be 11/16, plus 4/16 is going to be 15/16, plus 1 is going to be 16/16.
Yep.
So you always have your probabilities add up to 1. And so then if we graph that, this is a frequency distribution graph, and all I've done is graph those numbers there. And if we do a probability distribution graph, in this case it's going to have the same shape. We're just showing those fractions we're showing as percentages, but they're exactly the same thing. So 1 out of 16 is 6.25, etc., etc.
Right,
We're describing the same thing, and that's what's called a probability distribution. And it's not involved in every part of statistics, but it's most of statistics uses these. So the idea is 2 broad ways we'd use this. We'd kind of go, we're planning to do this. What's the chance of something happening? What's the chance of a particular outcome? Or, in terms of experimental, if nothing we're doing changes anything, makes a difference, this is what we expect to happen. So therefore, what are the chances of getting what actually happened? Was it just, it could have happened anyway within the range of possibilities? Or is that something which is really unexpected given what we expect to happen?
So this graph is an example of what you expect to happen.
Of what you expect to happen. This is a graph of what you expect to happen when you throw coins. You'd expect if you threw thousands and thousands of coins, it would end up having that
spread out
that kind of shape. It would actually end up having that kind of shape. Just a few things describing this kind of shape. We call that unimodal, which means it's got 1 peak, and it normally does. Normally it's sort of going to be more probable to get one thing and less probable to get other things. The time it doesn't, you can have bimodal or multimodal, but normally you'd think of 2 factors involved there. So it's likely that children under 5 will like this television show, and people over 80, you're going to assume they want something different out of it. So normally there'll be 2. Normally when there's just one thing's happening, it does end up being a unimodal graph. We also say that that's symmetrical. We'll come back to symmetrical. Different concept first. I'm getting ahead of myself. Now, supposing we want to know the chances of getting 2 or less throws, or two or less tails out of throwing the dice 4 times. We need to add those probabilities together. Or we've got 6.25% chance of getting nothing, 25% chance of getting 1, 37.5 chance of getting 2. So between them all together, it's going to be better than 50% chance. It's going to be, I don't know, I'd have to add that up. So that's called the cumulative distribution.
cumulative distribution.
Yeah, so we're looking at more than one thing happening. And if we wanted to work out the chances of getting 25 or 6.2, we can just subtract our cumulative from 1 because the whole thing's going to add up to 1.
Yep.
So now there's no need to remember about the binomial theorem for this. Just putting this in to illustrate a point. That is, when we looked at the binomial theorem, we looked at that number actually gets reversed, and there's an explanation for that in the book and why that is.
Okay.
The point here to say is that probability distributions normally have some sort of formula that describes them. In the book we go through a number of them. The book How to Love Statistics, when you haven't done the maths. And in this case it's going to be the same probabilities of adding h plus t together and raising them to whatever number of times, we've got like heads plus tails together, or the probabilities thereof. In the book we go into the detail that's for now. I just want to give you more of an intuitive sense of why that follows. When we have that sigma sign, you might remember when we looked at sigma notations, this is when you add things together. So that formula will give you the cumulative distribution. If we take that out, you've just got at any point you can plug those numbers in there and you'll get the answer.
Okay.
You can read the book or go back to the binomial theorem, or both if you want to know why that is.
Yeah.
But I want to illustrate that a little bit more intuitively and visually here about why we're going to get that number. If we think, and there's a guy called Francis Dalton who actually invented a device to do just this, to demonstrate the point. If we think about each of the toss of a coin as being like a ball bearing, you throwing the top of this, that could go left or right. And if it goes to the left, it's like hitting a head, and if you go to the right, it's like hitting a tail.
Okay.
And you're going to do that. So there's this combination of left or right choices that build up on one another.
Okay.
Is the idea. So if you want all heads, there's only one pathway that'll get there. You have to go head, 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 head.
Yeah.
If you want one tail, you could get there that way, that way, that way, or that way. 4 ways of getting there. And again, that is kind of what the binomial theorem is doing mathematically. If that isn't completely clear now, when you read the book, we expand on this in more detail. But similarly, if we wanted 2 tails, we could go, you could go 6 different ways of getting there, and so on and so on. For now, though, the thing to know is just that there is a formula that will describe a probability distribution.
Okay.
Generally, it's the key point there. Now, getting back to what I was started to talk about earlier, we call that graph symmetrical. So there's it looks even on either side. That isn't always the case in probability at all. Can be slanted to one side. If it's slanted to one side, we'd say it's skewed to the right. The skew, we talk about what's called the tail, how it goes. So if it's much more likely to get 0 than to 5, we'd say it's skewed right.
Okay. Could you get it going the other way?
It could absolutely go the other way, and it does all the time. They're often not symmetrical, can be slanted. We also call this discrete. Not discrete because it knows how to keep its mouth shut, but discrete, discrete, means it's in separate things. So that doesn't always happen. When we think about mathematics, we think about 2 concepts. It could be how many of something or how much of something. And how many is a discrete concept, 1, 2, 3, 4. How much could be anything. So how many years have I been alive for is different to how long have I been alive for. And similarly in probability, that these can be smooth curves. It's not and that's called continuous. The maths varies because when we're calculating things that are discrete, we use the theories, series and sums, and we use something called integral calculus when we need to work out the area under the curve. We haven't done that. But the main thing is they can be discrete or they can be continuous, and you have different mathematics in each case. That's probability distributions, or the introduction to them. Thank you for watching.